Hello viewers, as usual presenting a new topic. Let's start. Fuzzy logic, a fascinating branch of mathematics and computer science, offers a way to deal with uncertainty in decision making. Unlike regular logic, which is all about strict true or false statements, fuzzy logic embraces the fuzzy in between areas of truth. It's like saying something is kind of true or mostly false, which makes it perfect for handling real world situations where things are not always clear cut. Developed by Lotfi Zadeh in the 1960s, fuzzy logic has found its way into various fields like artificial intelligence and control systems because it can handle incomplete or ambiguous information really well. At its heart, fuzzy logic uses fuzzy sets and linguistic variables to represent vague ideas through membership functions that measure how much something belongs to a set. In this guide, we will explore fuzzy logic from the ground up, covering everything from basic concepts to practical applications. So whether you are a student, engineer, or researcher, you can dive into the world of fuzzy logic and discover its power in making sense of the uncertain. Fuzzy logic and artificial intelligence. Definition. Introduction to fuzzy logic. Fuzzy logic is a type of reasoning that deals with approximate rather than exact reasoning, unlike traditional binary logic, where something is either true or false. Fuzzy logic allows for intermediate values between true and false. This makes it suitable for modeling complex systems where the boundaries between categories are not clearly defined. Basic concepts of fuzzy logic. Fuzzy logic operates on the principle of degrees of truth. Instead of simply being true or false, statements can have varying degrees of truthfulness. This is achieved through the use of linguistic variables which allow us to describe values in terms of words rather than precise numbers. Fuzzy sets. Fuzzy sets are the building blocks of fuzzy logic. While traditional sets have crisp boundaries, fuzzy sets have fuzzy boundaries, allowing elements to belong to a set to a certain degree. This allows for a more flexible representation of uncertainty and ambiguity. Membership functions. Membership functions are used to determine the degree to which an element belongs to a fuzzy set. These functions map input values to membership degrees, which represent the degree of truth of a statement. Fuzzy logic operations. Fuzzy logic operations are used to manipulate fuzzy sets and make decisions based on fuzzy input. These operations include fuzzy and fuzzy or and fuzzy not, which operate on fuzzy sets in a way that reflects human reasoning. Applications of fuzzy logic. Fuzzy logic has a wide range of applications in various fields, including control systems, decision-making pattern recognition, and artificial intelligence. Its ability to handle uncertainty and ambiguity makes it particularly useful in situations where traditional logic may fall short. Advantages and disadvantages of fuzzy logic. Like any tool, fuzzy logic has its strengths and weaknesses. Some of its advantages include its ability to model human reasoning, handle imprecise data, and provide more flexibility in decision making. However, it can also be computationally expensive and may require careful tuning of parameters. Future directions of fuzzy logic. Fuzzy logic continues to evolve with ongoing research focused on improving its efficiency, scalability, and applicability to new domains. Future developments may involve integrating fuzzy logic with other artificial intelligence techniques, exploring its potential in emerging technologies, and refining its theoretical foundations. Understand the basics of fuzzy logic. Fuzzy logic is a form of logic that deals with reasoning that is approximate rather than precise. It's used in systems where ambiguity or uncertainty exists, making it particularly useful in situations where traditional binary logic true false falls short. Fuzzy sets. Unlike traditional sets where an element either belongs or does not belong, fuzzy sets allow for partial membership. Each element has a degree of membership between 0 and 1, indicating the degree to which the element belongs to the set. For example, in a fuzzy set representing tall people, someone who is 6 feet tall might have a membership value of 0.8, indicating a high degree of membership, while someone who is 5 feet tall might have a membership values of 0.3, indicating a lower degree of membership. Membership functions. Membership functions determine how each element is mapped to a degree of membership in a fuzzy set. These functions can take various shapes such as triangular, trapezoidal, Gaussian or sigmoidal curves. The choice of membership function depends on the nature of the problem and the characteristics of the data. For example, a triangular membership function might be used to represent medium temperature, where the peak of the triangle corresponds to the ideal or most typical value, and the width of the triangle determines the fuzziness or uncertainty. Fuzzy logic operators. Fuzzy logic introduces operators that can handle fuzzy sets. These include and, or, and not operators, which operate on fuzzy sets in a way that reflects the degree of membership of elements. For example, in fuzzy and, the degree of membership of an element in the result set is determined by the minimum of its degrees of membership in the input sets. Fuzzy rules. Fuzzy logic uses rules to describe relationships between input variables and output variables. These rules are expressed in the form of if-then statements, where the if part consists of fuzzy sets defined over input variables and the then part consists of fuzzy sets defined over output variables. Each rule has an associated weight or strength that determines its influence on the output. For example, a rule might state if temperature is cold and humidity is high, then increase heating, where cold and high are fuzzy sets defined over temperature and humidity respectively. Overall, fuzzy logic provides a framework for reasoning under uncertainty and imprecision, making it applicable in various fields such as control systems, decision making, pattern recognition, and artificial intelligence. Study mathematics basics. Set theory. Set theory is a branch of mathematics that deals with the study of collections of objects called sets and the relationships between them. Understanding sets, subsets, unions, intersections, and complements is fundamental. Sets can be finite or infinite, and they can contain elements of any type from numbers to symbols to other sets themselves. Probability theory. Probability theory is the study of randomness and uncertainty. It provides a framework for quantifying uncertainty and making predictions in situations where outcomes are uncertain. Sample space, the set of all possible outcomes of a random experiment. Event, a subset of the sample space. Probability measure, assign a probability to each event indicating the likelihood of that event occurring. Probability axioms, fundamental rules that govern probabilities such as non-negativity, normalization, and additivity. Probability distributions, functions that describe the likelihood of different outcomes in a random experiment. Common distributions include the uniform, normal, Gaussian, binomial, and Poisson distributions. Conditional probability, the probability of an event occurring given that an other event has already occurred. Independence, two events are independent if the occurrence of one does not affect the probability of the other. Bayes' theorem, a fundamental theorem in probability theory that describes how to update the probability of hypotheses based on new evidence, logic. While not strictly within set theory of probability theory, logic is a crucial component of mathematics. Understanding logical operators and or not, truth tables, quantifiers for all there exists, implications and equivalences is essential for rigorous mathematical reasoning. By mastering these foundational concepts in mathematics, you will develop the tools needed to tackle more advanced topics in fields such as statistics, machine learning, cryptography, and theoretical computer science. Learn Python or another programming language. Learn Python basics. If you are not already familiar with Python, start by learning the basics. Understand variables, data types, control structures, if statements, loops, functions, and object-oriented programming, classes, inheritance. Study fuzzy logic theory. Before diving into implementation, grasp the foundational concepts of fuzzy logic, including fuzzy sets, membership functions, fuzzy operators, and or not, fuzzy rules, and inference methods. Mamdani, Sugino. Choose a fuzzy logic library. Python offers several libraries for working with fuzzy logic. Scikit-fuzzy, a powerful library for fuzzy logic operations including fuzzy set creation, membership function generation, and fuzzy inference systems. pyfuzzy, an other library specifically designed for fuzzy logic, offering tools for fuzzy set operations, fuzzy inference, and system optimization. NumPy and matplotlib. While not dedicated to fuzzy logic, these libraries are often used in conjunction with fuzzy logic implementations for numerical operations and visualization. Practice implementing fuzzy logic systems. Start by implementing simple fuzzy logic systems to get a feel for how the concepts translate into code. Build systems for tasks such as temperature control, speed regulation, or decision making based on fuzzy rules. Why logic is applied in real world scenarios. This could include applications in control systems, pattern recognition, decision support systems, and artificial intelligence. Experiment and iterate. As you gain more experience, experiment with different membership functions, rule sets, and inference methods to see how they affect system behavior. Iterate on your implementations to improve performance and accuracy. Explore fuzzy logic libraries. Scikit-fuzzy. Description. Scikit-fuzzy is a powerful library for fuzzy logic operations in Python. It provides tools for fuzzy set creation, membership function generation, fuzzy inference systems, and diffusification methods. Features. Membership functions. Triangular, trapezoidal, Gaussian, etc. Fuzzy inference methods. Mamdani Sugino, weighted average. Takagi Sugino Kang, TSK models. Diffusification methods. Centroid mean of maximum MOM, weighted average. Fuzzy control systems Tools for building fuzzy logic controllers for various applications. Documentation. The official documentation provides comprehensive guides, tutorials, and examples for using scikit-fuzzy in fuzzy logic applications. Installation. You can install scikit-fuzzy using pip. Copy code pip install scikit-fuzzy. pyfuzzy. Description. pyfuzzy is another Python library specifically designed for fuzzy logic. It offers tools for fuzzy set operations, fuzzy inferences, system optimization, and visualization. Features. Fuzzy set operations, union intersection complement, fuzzy inference methods, Memdani, Sugino optimization algorithms, genetic algorithms, simulated annealings, visualization tools, plotting membership functions, rules, surfaces, documentation. pyfuzzy provides documentation with usage examples and tutorials to help users get started with fuzzy logic implementations. Installation. pyfuzzy can be installed via pip. Copy code pip install pyfuzzy. scipy and numpy. Description. While not dedicated to fuzzy logic, Scipy and NumPy are fundamental libraries for numerical computing in Python. They provide tools for mathematical operations, array manipulation, optimization, and integration, which are often used in conjunction with fuzzy logic implementations. Features. Numerical operations, linear algebra, statistical functions, Fourier transforms. Optimization algorithms, root finding, curve fitting. Integration, numerical integration, differential equations solving. Documentation, both Scipy and NumPy have extensive documentation with examples and tutorials for various numerical computing tasks. Installation, Scipy and NumPy are commonly installed together using copy code pip install Scipy NumPy. These libraries provide a solid foundation for implementing fuzzy logic systems in Python, each offering unique features and capabilities to suit different needs and preferences. Dive into rule-based systems. Fuzzy sets. Construction. Fuzzy sets are defined over input and output variables by specifying membership functions that quantify the degree of membership of elements in the sets. These membership functions can take various shapes such as triangular, trapezoidal, Gaussian, and sigmoidal curves depending on the nature of the variables and the problem domain. Interpretation. Fuzzy sets allow for the representation of linguistic variables, that is hot, cold, medium, enabling a more human-like approach to reasoning and decision making. The interpretation of fuzzy sets involves understanding the meaning of linguistic terms and their corresponding membership degrees. Fuzzy rules. Construction. Fuzzy rules are expressed in the form of if-then statements that relate input variables to output variables. Each rule consists of an attendant, the if part, and a consequent, the then part. The attendant typically consists of one or more fuzzy sets defined over input variables, while the consequent consists of fuzzy sets defined over output variables. Interpretation. Fuzzy rules encode expert knowledge or heuristics about how inputs should be mapped to outputs in a given context. These rules are often derived from human expertise or domain knowledge and are represented in a form that is understandable and interpretable by humans. Fuzzy inference engine. Construction. The fuzzy inference engine applies fuzzy rules to input data to generate output values. This involves several steps, including fuzzification, converting crisp input values to fuzzy sets, rule evaluation, determining the degree to which each rule is satisfied. Aggregation, combining the outputs of multiple rules, and diffusification, converting fuzzy output sets to crisp values. Interpretation, the fuzzy inference engine mimics human reasoning by combining fuzzy rules and input data to generate output values that reflect the uncertainty and imprecision inherent in the problem domain. The interpretation of the output values depends on the application and may involve further processing or decision making. Overall, rule-based systems in fuzzy logic provide a flexible framework for modeling complex relationships and making decisions in uncertain or imprecise environments. By constructing and interpreting fuzzy sets, fuzzy rules, and a fuzzy inference engine, these systems enable a more natural and intuitive approach to reasoning and decision making compared to traditional crisp logic systems. Understanding fuzzy inference system (FIS). Fuzzification. Description. Fuzzification is the process of converting crisp input values into fuzzy sets, enabling them to be used as inputs to the fuzzy inference system. Crisp values are often imprecise or uncertain, and fuzzification allows them to be represented as linguistic variables with membership degrees. Implementation. In the fuzzification stage, each crisp input value is mapped to one or more fuzzy sets using their corresponding membership functions. This results in a degree of membership for each input variable in each fuzzy set. Example. For example, if the input variable is temperature and the crisp value is 25 centigrade, it might have a high degree of membership in the fuzzy set, hot, and a low degree of membership in the fuzzy set, warm. Rule evaluation. Description. Rule evaluation involves determining the degree to which each fuzzy rule in the rule base is satisfied given the fuzzy sets obtained from the fuzzification stage. This is done by evaluating the antecedent if part of each rule and determining the strength of the rule's activation. Implementation. In the rule evaluation stage, the degree of satisfaction of each rule is calculated based on the degree of membership of the input variables in the fuzzy sets defined in the antecedent of the rule. This is often done using fuzzy logic operators such as and, or, and, not to combine the membership degrees of the input variables. Example, if a rule states if temperature is hot and humidity is high, then output is very hot. The rule evaluation stage calculates the degree to which both temperature is hot and humidity is high are true. Diffusification. Description. Diffusification is the process of converting the fuzzy output sets obtained from the rule evaluation stage into crisp output values that can be used for decision making or control purposes. This involves determining a single representative value or point from the fuzzy output sets. Implementation. In the diffusification stage, various methods can be used to compute a crisp output value from the fuzzy output sets, such as centroid, mean of maximum, MOM, weighted average, or other custom methods. Each method provides a different way of summarizing the fuzzy output sets. Example, if the fuzzy output sets represent linguistic variables like low, medium, and high, diffusification determines a crisp output value that best represents the overall output of the fuzzy inference system. By incorporating these components, fuzzification, rule evaluation, and diffusification, a fuzzy inference system can effectively process uncertain or imprecise inputs and generate meaningful outputs, making it a powerful tool for decision making, control systems, and pattern recognition in various domains. Study fuzzy logic controllers, FLC. Fuzzy logic control, FLC, is a powerful approach used in control systems to handle complex, nonlinear, and uncertain systems. FLC uses fuzzy logic to mimic human decision-making processes, enabling the control system to adapt and respond effectively to changing conditions. Fuzzy logic control, FLC, design process. System modeling. The first step in designing an FLC is to model the system being controlled. This involves identifying the input and output variables, defining the rules governing their relationship, and characterizing the behavior of the system. Fuzzification. Crisp input data from sensors or other sources are fuzzified into fuzzy sets using membership functions. This step involves mapping the crisp input values to linguistic variables with degrees of membership in corresponding fuzzy sets. Rule-based construction. Based on domain knowledge or expert input, a rule base is constructed to relate the fuzzy input variables to the fuzzy output variables. Each rule in the rule base defines a specific control action based on the current state of the system. Rule evaluation. The fuzzy input variables are evaluated against the rules in the rule base to determine the degree to which each rule is satisfied. This involves applying fuzzy logic operators and or to combine the membership degrees of the input variables according to the antecedents of the rules. Aggregation. The outputs of all activated rules are aggregated to obtain a fuzzy output set. This step involves combining the outputs of individual rules to form a comprehensive representation of the system's response. Diffusification. The fuzzy output set is diffusified to obtain a crisp output value that can be used to control the system. Various diffusification methods such as centroid mean of maximum MOM or weighted average can be employed to compute the crisp output value. Applications of fuzzy logic control, FLC. Temperature control. FLC is commonly used in heating, ventilation, and air conditioning HVAC systems to regulate temperature efficiently and maintain comfort levels in buildings. Speed control. FLC can be applied in automotive systems to control vehicle speed, especially in situations where precise control is required, such as cruise control or adaptive cruise control. Process control. FLC is used in industrial processes such as chemical plants and manufacturing to regulate parameters like pressure, flow rate, and temperature in real time, optimizing efficiency and ensuring product quality. Robotics. FLC plays a vital role in robotic systems for navigation, trajectory planning, and obstacle avoidance, enabling robots to operate effectively in dynamic environments. Consumer electronics. FLC is used in various consumer electronics devices such as washing machines, refrigerators, and smart thermostats to provide intelligent and adaptive control based on user preferences and environmental conditions. Overall, FLC offers a flexible and intuitive approach to control systems design, making it suitable for a wide range of applications where traditional control methods may be inadequate. Its ability to handle uncertainty and imprecision makes it particularly well suited for complex and non-linear systems encountered in real-world scenarios. Explore applications of fuzzy logic. Fuzzy logic finds numerous real-world applications across various domains due to its ability to handle uncertainty, imprecision, and complexity. Medical diagnosis. Fuzzy logic is used in medical diagnosis systems to interpret patient symptoms and make diagnostic decisions by modeling uncertainty and vagueness inherent in medical data. Fuzzy logic systems can provide more nuanced and accurate diagnosis, especially in cases where symptoms are ambiguous or overlapping. Financial risk assessment. In finance, fuzzy logic is employed for risk assessment and decision making in investment portfolios. Fuzzy logic models can incorporate multiple factors such as market volatility, economic indicators, and investor sentiment to evaluate the risk associated with different investment options and optimize portfolio allocations. Consumer electronics. Fuzzy logic is used in consumer electronics devices such as washing machine, air conditioners, and refrigerators to make adaptive and intelligent decisions based on user preferences and environmental conditions. For example, washing machines equipped with fuzzy logic can adjust wash cycle, water temperature, and detergent dosage according to the type and amount of laundry. Control systems. Automotive systems. Fuzzy logic control is widely employed in automotive systems for tasks such as engine management, transmission control, and vehicle stability control. Fuzzy logic controllers can adaptively adjust control parameters in real time to optimize performance, fuel efficiency, and safety, especially in situations where traditional control methods may be inadequate. Industrial automation. Fuzzy logic is used in industrial automation and process control systems to regulate parameters such as temperature, pressure, flow rate, and pH level in manufacturing processes. Fuzzy logic controllers can handle non-linearities, uncertainties, and time delays inherent in industrial systems, improving process efficiency and product quality. Traffic management. Fuzzy logic based traffic control systems are deployed in urban transportation networks to optimize traffic flow, reduce congestion, and minimize travel time by dynamically adjusting traffic signal timings and coordinating signalized intersections. Fuzzy logic controllers can adapt to changing traffic conditions and improve overall system performance. Artificial intelligence. Pattern recognition. Fuzzy logic is used in pattern recognition and classification tasks such as image processing, speech recognition, and handwriting recognition. Fuzzy logic classifiers can handle uncertainty and variability in input data, making them robust to noise, distortion, and occlusion. Robotics. Fuzzy logic plays a crucial role in robotics systems for tasks such as navigation, path planning, and obstacle avoidance. Fuzzy logic controllers enable robots to make intelligent decisions based on sensor input and environmental conditions, allowing them to operate autonomously in complex and dynamic environments. Natural language processing. Fuzzy logic techniques are applied in natural language processing tasks such as sentiment analysis, information retrieval, and text summarization. Fuzzy logic models can capture the ambiguity and vagueness inherent in human language, improving the accuracy and reliability of language processing systems. These are just a few examples of how fuzzy logic is applied in real-world scenarios across decision-making, control systems, and artificial intelligence. Its ability to model and reason with uncertain and imprecise information makes it a valuable tool in diverse applications where traditional methods may fall short. Fuzzy logic and artificial intelligence integration. Fuzzy logic can be integrated with other artificial intelligence techniques such as machine learning and expert systems to enhance their capabilities and address complex problems more effectively. Integration with machine learning. Fuzzy inference systems and machine learning models. Fuzzy logic can be used to interpret and explain the outputs of machine learning models, especially in domains where interpretability is critical, such as healthcare and finance. Fuzzy inference systems can provide human understandable explanations for the decisions made by machine learning models, helping to build trust and confidence in their predictions. Fuzzy clustering. Fuzzy clustering techniques such as fuzzy C-means FCM can be used to partition data into clusters with overlapping boundaries. These fuzzy clusters can then be used as input features for machine learning algorithms, allowing them to handle data with uncertainty and ambiguity more effectively. Fuzzy rule-based classification. Fuzzy logic can be applied in conjunction with machine learning algorithms to build fuzzy rule-based classifiers. These classifiers use fuzzy rule to classify instances based on their features, incorporating domain knowledge or expert heuristics into the classification process. Fuzzy rule-based classifiers can handle uncertainty and imprecision in the data, improving classification accuracy, especially in domains with noisy or incomplete data. Integration with expert systems. Fuzzy expert systems. Expert systems combine human expertise with computational techniques to solve complex problems in specific domains. Fuzzy logic can be integrated into expert system to model the uncertainty and imprecision inherent in human decision-making processes. Fuzzy expert systems use fuzzy rules and fuzzy inference to emulate the reasoning of human experts, allowing them to make intelligent decisions in uncertain or ambiguous situations. Hybrid expert systems. Hybrid expert systems combine multiple artificial intelligence techniques such as fuzzy logic, rule-based reasoning, and machine learning to leverage the strengths of each approach. Fuzzy logic can be used in conjunction with other techniques in hybrid expert systems to handle uncertainty, interpretability, and complex reasoning more effectively. For example, fuzzy logic can be used to interpret the outputs of machine learning models or to guide the decision-making process in rule-based expert systems. Fuzzy logic control in expert systems. Expert systems often involve control and decision-making processes where fuzzy logic can be applied to model the uncertainty and imprecision in the decision space. Fuzzy logic controllers can be integrated into expert systems to regulate and optimize the behavior of the system in response to changing conditions or user preferences. By integrating fuzzy logic with other artificial intelligence techniques such as machine learning and expert systems, we can build more robust, adaptable, and intelligent systems that can handle uncertainty, complexity, and ambiguity in real-world applications. Hands-on implementation. Temperature control system. Objective: design a fuzzy logic-based temperature control system for a heating or cooling device. Implementation: define linguistic variables for temperature, that is cold, warm, hot, and corresponding membership functions. Create fuzzy rules to map temperature values to control actions, that is increase heating, decrease cooling. Implement fuzzification, rule evaluation, aggregation, and diffusification stages using a programming language like Python and a library such as scikit-fuzzy. Test the system with different temperature inputs and evaluate its performance in maintaining the desired temperature. Car speed control system. Objective: develop a fuzzy logic-based speed control system for an autonomous vehicle or cruise control system. Implementation: define linguistic variables for speed, that is slow, moderate, fast, and corresponding membership functions. Create fuzzy rules to map speed values to throttle or brake actions based on road conditions, traffic, and driver preferences. Implement the fuzzy inference engine using Python and a library like scikit-fuzzy to determine the appropriate throttle, or brake input. Test the system in a simulation environment or on a physical vehicle platform to evaluate its performance in maintaining safe and efficient speed control. Traffic light control system objective. Design a fuzzy logic based traffic light control system to optimize traffic flow and reduce congestion at intersections. Implementation. Define linguistic variables for traffic flow, queue length, and signal timing, that is green, yellow, red, and corresponding membership functions. Create fuzzy rules to dynamically adjust signal timings based on traffic conditions, pedestrians crossings, and vehicle queues. Implement the fuzzy inference engine to determine the optimal signal timings for each phase of the traffic light cycle. Test the system using traffic simulation software or in a real-world traffic intersection to assess its effectiveness in improving traffic flow and reducing delays. These project ideas provide opportunities to apply fuzzy logic concepts and techniques to solve real-world problems in control systems, decision-making, and artificial intelligence. By implementing these projects, you can gain practical experience in developing fuzzy logic systems and enhance your understanding of their applications. Experiment with fuzzy clustering. Fuzzy clustering algorithms are used for data classification and pattern recognition tasks where data points may belong to multiple clusters with varying degrees of membership. Unlike traditional clustering algorithms like k-means, which assign each data point to a single cluster, fuzzy clustering algorithms assign each data point membership degrees to multiple clusters. Fuzzy C-means FCM. FCM is one of the most widely used fuzzy clustering algorithms. It extends the k-means algorithm by allowing data points to belong to multiple clusters simultaneously. In FCM, each data point has membership degrees for each cluster, indicating the degree of belongingness. The algorithm iteratively updates cluster centroids and membership degrees until convergence, minimizing the objective function which measures the difference between data points and cluster centroids weighted by membership degrees. Possibilistic C-means PCM. PCM is an extension of FCM that introduces a relaxation parameter to control the fuzziness of the clusters. Unlike FCM, which assumes Gaussian membership functions, PCM uses possibility distributions to model the degree of membership of data points to clusters. PCM allows for a more flexible representation of uncertainty and can handle outliers and noise better than FCM. Gustafsson-Castle GK algorithm. GK algorithm is a fuzzy clustering algorithm that considers both the covariance and distance between data points and cluster centroids. It defines a fuzzy covariance matrix for each cluster, which accounts for the shape and orientation of the cluster. GK algorithm adapts the cluster shapes to the data distribution and can handle elongated or irregularly shaped clusters. Fuzzy Gaussian mixture model FGMM. FGMM is a probabilistic model-based fuzzy clustering algorithm that assumes data points are generated from a mixture of Gaussian distributions. It extends the Gaussian mixture model GMM by incorporating fuzzy membership degrees to model the uncertainty in cluster assignments. FGMM iteratively estimates the parameters of the Gaussian components and the membership degrees of data points to each component using the expectation maximization EM algorithm. Fuzzy Possibilistic C-means FPCM. FPCM is a hybrid fuzzy clustering algorithm that combines the ideas of FCM and PCM. It introduces two parameters, the fuzzifier and the relaxation parameter, to control the trade-off between cluster fuzziness and robustness to noise. FPCM provides a flexible framework for clustering data with varying degrees of uncertainty and noise. These fuzzy clustering algorithms are widely used in data mining, pattern recognition, image segmentation, and other areas where traditional clustering methods may not perform well due to the presence of uncertainty and ambiguity in the data. By allowing data points to belong to multiple clusters with varying degrees of membership, fuzzy clustering algorithms provide a more nuanced and flexible approach to data classification and pattern recognition. Understand fuzzy neural networks. The integration of fuzzy logic with neural networks combines the strengths of both approaches to enhance decision-making capabilities, especially in handling complex, uncertain, and imprecise data. This hybrid approach, often referred to as fuzzy neural networks (FNNS) or neuro-fuzzy systems, leverages the learning capabilities of neural networks and the reasoning capabilities of fuzzy logic to build more robust and adaptive systems. Fuzzy inference system (FIS) as activation function. In traditional neural networks, activation functions are typically deterministic and non-fuzzy, such as sigmoid or ReLU functions. In fuzzy neural networks, fuzzy inference systems can be used as activation functions to introduce fuzzy reasoning and decision-making capabilities into the network. Fuzzy activation functions map input values to fuzzy sets and compute the degree of membership in each set, allowing the network to handle uncertainty and imprecision in the input data. Hybrid learning algorithms. Fuzzy neural networks use hybrid learning algorithms that combine the backpropagation algorithm used in neural networks with fuzzy inference techniques used in fuzzy logic. During training, the network learns to adjust its parameters, weights, and biases using gradient descent to minimize the loss function while also updating the fuzzy inference system's rules and membership functions based on the training data. This hybrid approach enables the network to learn from both crisp and fuzzy data, adapt to changing conditions, and make decisions based on fuzzy rules and linguistic variables. Adaptive fuzzy neural networks. Adaptive fuzzy neural networks dynamically adjust their fuzzy inference systems and neural network architectures based on the input data and task requirements. These networks can automatically generate or refine fuzzy rules and membership functions during training or operation, allowing them to adapt to different environments and problem domains. Adaptive fuzzy neural networks are particularly useful for online learning and real-time decision-making applications, where the data distribution may change over time. Applications. Fuzzy neural networks have been successfully applied in various domains including pattern recognition, control systems, forecasting optimization, and decision support systems. Examples of applications include fault diagnosis in industrial processes, medical diagnosis systems, financial forecasting models, intelligent control systems, and autonomous vehicles. By integrating fuzzy logic with neural networks, fuzzy neural networks offer a flexible and powerful framework for modeling complex systems, reasoning with uncertain and imprecise data, and making decisions in real-world applications. The hybrid approach combines the learning capabilities of neural networks with the interpretability and reasoning capabilities of fuzzy logic, resulting in more robust, adaptive, and intelligent systems. Explore evolutionary algorithms and fuzzy systems. Evolutionary algorithms, EAS, are optimization techniques inspired by the process of natural selection and evolution. They involve iteratively searching for the best solutions to optimization problems by simulating the process of genetic variation, selection, and reproduction. When combined with fuzzy systems, evolutionary algorithms can be used to optimize fuzzy inference systems (FIS) and improve their performance in various tasks. Parameter optimization. Fuzzy inference systems contain parameters such as membership functions, rule weights, and rule thresholds that need to be tuned for optimal performance. Evolutionary algorithms can be used to search for the best set of parameters by treating them as candidate solutions in a population. During each generation, the evolutionary algorithm evaluates the fitness of each candidate solution based on its performance on a validation dataset or an objective function. Through the process of selection, crossover, and mutation, the evolutionary algorithm iteratively evolves the population of candidate solutions towards better performing solutions. Rule-based optimization. The rule base of a fuzzy inference system consists of fuzzy rules that relate input variables to output variables. Evolutionary algorithms can be employed to optimize the structure and content of the rule base by evolving a population of candidate rule sets. Each candidate rule set represents a potential configuration of fuzzy rules, including the number of rules, their antecedents, consequents, and associated parameters. The evolutionary algorithm evaluates the fitness of each candidate rules set based on its ability to accurately model the system behavior and make correct predictions. By iteratively evolving the population of candidate rule sets, the evolutionary algorithm identifies the most effective rules base for the given optimization task. Feature selection. In many optimization tasks, the number of input variables may be large, leading to high-dimensional feature spaces and computational complexity. Evolutionary algorithms can be used for feature selection by searching for subsets of input variables that are most relevant to the optimization task. By treating different subsets of input variables as candidate solutions, the evolutionary algorithm evaluates the fitness of each subset based on its impact on the performance of the fuzzy inference system. Through the process of selection, crossover, and mutation, the evolutionary algorithm identifies the subset of input variables that leads to the best performance on the optimization task. Hybrid approaches. Evolutionary algorithms can be combined with other optimization techniques such as gradient descent, simulated annealing, or practical swarm optimization to enhance the efficiency and effectiveness of optimization tasks involving fuzzy systems. Hybrid approaches leverage the complementary strengths of different optimization techniques to overcome their respective limitations and archive better results. By integrating evolutionary algorithms with fuzzy systems, optimization tasks such as parameter tuning, rule-based optimization, and feature selection can be effectively addressed, leading to improved performance and robustness in various applications of fuzzy logic. Study fuzzy control in robotics. Fuzzy logic plays a significant role in robotic systems, particularly in control and decision-making processes where uncertainty, imprecision, and dynamic environments are common challenges. Control systems. Motion control. Fuzzy logic is used in robotic motion control systems to adjust motor speeds, trajectories, and joint angles based on sensor feedback and task requirements. Fuzzy controllers can handle non-linearities and uncertainties in the robot's dynamics, allowing for smoother and more adaptive motion control. Manipulator control. Fuzzy logic applied in manipulator control to regulate the position, orientation, and force exerted by robot manipulators during tasks such as grasping, lifting, and manipulation. Fuzzy controllers can adjust the stiffness and damping of robot joints in real time to accommodate variations in object shape, size, and weight. Mobile robot navigation. Fuzzy logic is used in mobile robot navigation systems to plan and execute collision-free paths in dynamic and uncertain environments. Fuzzy controllers can integrate inputs from sensors such as cameras, lidar, and ultrasonic sensors to make real-time decisions about steering, speed, and obstacle avoidance. Decision making. Path planning. Fuzzy logic is applied in path planning algorithms to generate optimal or near optimal paths for robots to navigate in complex environments. Fuzzy controllers consider factors such as distance to obstacles, terrain roughness, and safety margins to select the most suitable path for the robot. Task allocation. In multi-robot systems, fuzzy logic is used for task allocation and coordination to optimize the allocation of tasks among robots based on their capabilities, energy levels, and proximity to tasks. Fuzzy controllers can dynamically adjust task assignments to balance workload and minimize completion time. Fault diagnosis and recovery. Fuzzy logic is utilized in fault diagnosis and recovery systems to detect, diagnose, and mitigate faults or failures in robotic components or subsystems. Fuzzy inference systems can analyze sensor data and system states to identify anomalies and trigger appropriate responses or recovery strategies. Human-robot interaction. Emotion recognition. Fuzzy logic is applied in emotion recognition systems to interpret human emotions and intentions based on facial expressions, gestures, and speech patterns. Fuzzy inference systems can analyze multimodal data to infer the emotional state of human users and adapt robot behavior accordingly. Behavior generation. Fuzzy logic is used in behavior generation systems to generate human-like or socially appropriate behaviors for robots in human-robot interaction scenarios. Fuzzy controllers can adjust parameters such as speech rate, gesture intensity, and gaze direction to convey different social cues and facilitate effective communication with humans. Overall, fuzzy logic provides a flexible and intuitive framework for modeling and controlling robotic systems in dynamic and uncertain environments. By incorporating fuzzy logic into control and decision-making processes, robotic systems can adapt and respond effectively to changing conditions, achieve robust performance, and interact seamlessly with humans in various applications. Fuzzy logic can work in tandem with machine learning techniques to enhance their capabilities and address problems involving uncertainty, imprecision, and ambiguity in data. Machine learning. Fuzzy membership functions in feature engineering. Fuzzy logic can be used in feature engineering to define fuzzy membership functions for input variables. These membership functions capture the degree of membership or belongingness of data points to different categories or classes. By incorporating fuzzy membership functions into feature representation, machine learning models can better handle uncertain or ambiguous data and capture complex relationships between variables. Fuzzy rule-based systems as interpretable models. Fuzzy rule-based systems provide interpretable models that represent human-like reasoning and decision-making processes using linguistic variables and fuzzy rules. Machine learning algorithms such as decision trees or rule induction algorithms can be combined with fuzzy logic to learn fuzzy rule-based models from data. These models offer transparency and explainability, making them suitable for applications where understanding the decision process is important, such as medical diagnosis or expert systems. Fuzzy inference systems for data fusion. Fuzzy inference systems can be used for data fusion in machine learning tasks where data from multiple sources or modalities need to be integrated. FIS aggregate information from different sources using fuzzy rules and combine them to make decisions or predictions. By incorporating fuzzy inference systems into machine learning pipelines, models can effectively handle heterogeneous data sources and extract meaningful insights from diverse datasets. Fuzzy clustering for unsupervised learning. Fuzzy clustering algorithms such as fuzzy C-means FCM can be used for unsupervised learning tasks where data points may belong to multiple clusters with varying degrees of membership. Fuzzy clustering algorithms provide a flexible and robust approach to clustering data in complex and overlapping clusters. Machine learning algorithms can leverage fuzzy clustering results to segment data and identify underlying patterns or structures in the data. Fuzzy logic control in reinforcement learning. Fuzzy logic control (FLC) can be integrated with reinforcement learning algorithms to guide the exploration and exploitation of actions in dynamic environments. Fuzzy logic controllers can provide a principal approach to decision making and action selection, especially in situations where the system dynamics are uncertain or poorly understood. By combining fuzzy logic control with reinforcement learning techniques, agents can learn to adapt their behavior in real time based on fuzzy rules and feedback from the environment. Overall, integrating fuzzy logic with machine learning techniques provide a powerful framework for addressing complex and uncertain problems, enhancing model interpretability and improving decision-making capabilities in various applications. Fuzzy logic as activation functions. Traditionally, neural networks use deterministic activation functions like sigmoid or ReLU to introduce non-linearity into the network. However, these functions may not effectively handle uncertainty and imprecision in input data. Fuzzy logic offers an alternative by providing fuzzy activation functions. These functions can handle input data that is not clearly defined or falls into vague categories. By using fuzzy activation functions, neural networks can better accommodate uncertain or imprecise input data, leading to more robust performance, especially in tasks where data ambiguity is prevalent. Integration as neurofuzzy systems or fuzzy neural networks. Neurofuzzy systems or fuzzy neural networks combine the strengths of both fuzzy logic and neural networks. In these hybrid systems, neural networks are used for learning and pattern recognition, while fuzzy logic is employed to interpret and process the outputs generated by the neural networks. This integration enables a more interpretable and transparent decision-making process. Instead of black box outputs, where it's unclear why a certain decision was made, neurofuzzy systems provide explanations based on fuzzy logic rules, making the decision-making process more understandable to humans. This is particularly important in critical applications such as medical diagnosis or financial forecasting, where transparency and interpretability are essential. Learning fuzzy rules or membership functions. Neural networks have the ability to learn fuzzy rules or membership functions from data. This means that instead of relying solely on manually crafted fuzzy rules, neural networks can automatically infer these rules from data during the learning process. This capability allows neural networks to capture complex relationships and patterns in the data that may be difficult to model using traditional fuzzy logic techniques alone. By learning fuzzy rules or membership functions, neural networks can adapt to the underlying data distribution more effectively, leading to improved performance in tasks where complex and non-linear relationships exist. In summary, integrating fuzzy logic with neural networks offers several advantages, including enhanced handling of uncertain and imprecise data, improved interpretability of decision-making processes, and the ability to capture complex relationships and patterns in the data more effectively. This integration opens up new possibilities for applications in areas such as natural language processing (NLP), where dealing with ambiguity and uncertainty is inherent. Deep learning. Fuzzy logic can complement deep learning techniques by providing interpretability and explainability to complex deep learning models. Deep neural networks often lack transparency, making it challenging to understand the reasons behind their predictions. By incorporating fuzzy logic into deep learning models, the decision-making process becomes more interpretable and understandable. Fuzzy logic can also be used in the pre-processing or post-processing stages of deep learning pipelines to handle uncertain or imprecise data, clean noisy data, or refine the outputs of deep learning models. Natural language processing. Fuzzy logic can be applied in natural language processing tasks such as sentiment analysis, text classification, and information retrieval to handle the inherent uncertainty and ambiguity in natural language data. Fuzzy logic techniques such as fuzzy matching and fuzzy clustering can be used to compare and categorize text data based on similarity or proximity, allowing for more flexible and nuanced analysis of text documents. Fuzzy logic can also be integrated with deep learning models for natural language processing tasks, where it can provide linguistic variables and fuzzy rules to interpret and explain the outputs of deep learning models, making them more interpretable and transparent. Overall, fuzzy logic can be seamlessly integrated with neural networks, deep learning, and NLP techniques to address complex problems involving uncertainty, imprecision, and ambiguity in data. By combining these techniques, researchers and practitioners can develop more robust, interpretable, and intelligent systems for a wide range of applications. Reinforcement learning. Fuzzy logic can be integrated with various machine learning and data processing techniques, including reinforcement learning, decision trees, support vector machines (SVM), clustering algorithms, APIs, and data pre-processing methods. Reinforcement learning is a machine learning paradigm where an agent learns to make decisions by interacting with an environment. The agent receives feedback in the form of rewards or penalties based on its actions, and its goal is to maximize the cumulative reward over time. Fuzzy logic, on the other hand, is a mathematical framework for dealing with uncertainty and imprecision in decision making. When applied to reinforcement learning, fuzzy logic provides a structured way to handle the complexity and uncertainty of real world environments. Decision making and action selection. In reinforcement learning, the agent needs to make decisions about which actions to take based on its current state. Fuzzy logic can help by providing a principal approach to decision making in dynamic and uncertain environments. Instead of CRISP, binary decisions, fuzzy logic allows for gradual transitions between different actions, making it well suited for situations where the optimal action is not always clear cut. Guiding exploration and exploitation. Reinforcement learning agents often face the dilemma of exploration versus exploitation, where they need to balance trying out new actions, exploration, with exploiting actions that are known to yield high rewards, exploitation. Fuzzy logic controllers can help guide this process by adjusting membership functions and fuzzy rules based on feedback from the environment. This allows the agent to explore different actions while also exploiting the ones that have shown promise in the past. Handling complexity. Real-world decision-making tasks can be highly complex with numerous variables and uncertainties to consider. Fuzzy reinforcement learning techniques combine the learning capabilities of reinforcement learning with the reasoning capabilities of fuzzy logic to tackle these complex tasks. By integrating fuzzy logic into the reinforcement learning framework, agents can make more informed and nuanced decisions in challenging environments. Overall, using fuzzy logic in reinforcement learning allows agents to navigate dynamic and uncertain environments more effectively, make better decisions in complex tasks, and strike a balance between exploration and exploitation. This combination of reinforcement learning and fuzzy logic can be particularly useful in domains where traditional approaches struggle to cope with uncertainty and ambiguity. Decision trees. Fuzzy logic can indeed enhance decision trees by addressing uncertainty and imprecision in the input data or class labels. Handling uncertainty and imprecision in traditional decision trees, data is partitioned into crisp binary splits based on precise thresholds or conditions. However, real-world data often contains uncertainty and imprecision. Fuzzy logic allows decision trees to handle this by using fuzzy sets and fuzzy rules to represent conditions at each node. Instead of strict cutoff points, fuzzy sets allow for gradual transitions, enabling decision trees to capture the uncertainty inherent in the data more effectively. Extension of traditional decision trees. Fuzzy decision trees extend traditional decision trees by incorporating fuzzy sets and fuzzy rules. Each node in a fuzzy decision tree represents a fuzzy set, and the conditions for splitting the data into child nodes are expressed as fuzzy rules. This extension allows decision trees to handle fuzzy or imprecise data more naturally and flexibly, capturing non-linear relationships and complex decision boundaries. Fuzzy decision tree excel at capturing non-linear relationships and complex decision boundaries in the data. Traditional decision trees may struggle with datasets where the relationships between variables are not linear or where decision boundaries are intricate. Fuzzy decision trees can represent these relationships and boundaries more accurately by allowing for fuzzy logic-based conditions, leading to more accurate and interpretable models. Overall, fuzzy decision trees provide a powerful framework for handling uncertainty and imprecision in data, extending traditional decision trees to capture complex relationships and decision boundaries. By incorporating fuzzy logic principles, these models can produce more accurate and interpretable results, particularly in scenarios where traditional methods may fall short. Support vector machines (SVM). Fuzzy logic can be integrated with SVMs to handle imbalanced or overlapping classes in the data. Fuzzy SVMs use fuzzy membership functions to represent the degree of belongingness of data points to different classes, allowing for more flexible and robust classification. Fuzzy SVMs can also incorporate fuzzy rules to model non-linear relationships between input features and class labels, improving the performance of the classifier. Clustering algorithms. Fuzzy logic can enhance clustering algorithms such as k-means and fuzzy c-means (FCM) by allowing data points to belong to multiple clusters with varying degrees of membership. Fuzzy clustering algorithms use fuzzy sets and fuzzy rules to assign data points to clusters, enabling more flexible and nuanced clustering of data. Fuzzy clustering techniques are particularly useful in applications where data points may have ambiguous or overlapping cluster assignments. APIs and data pre-processing. Fuzzy logic can be used in APIs and data pre-processing pipelines to handle uncertain or imprecise data, clean noisy data, and make decisions based on fuzzy rules. Fuzzy logic techniques such as fuzzy matching, fuzzy inference, and fuzzy clustering can be integrated into data processing workflows to improve the quality and reliability of data analysis and decision making. Overall, fuzzy logic can be applied across a wide range of machine learning and data processing techniques to handle uncertainty, imprecision, and ambiguity in data, leading to more robust and flexible models and systems. Data mining. Fuzzy logic is indeed a valuable tool in data mining for handling uncertainty and imprecision in the data, particularly when dealing with noisy, incomplete, or ambiguous datasets. Handling uncertainty and imprecision in data mining, the quality of the data can often be compromised by noise, missing values, or ambiguity. Fuzzy logic provides a framework to represent and reason with uncertainty in the data by allowing for gradual transitions and degrees of membership. Fuzzy logic can accommodate uncertain or imprecise data more effectively than traditional crisp logic approaches. Fuzzy clustering algorithms. Fuzzy clustering algorithms such as fuzzy c-means (FCM) are widely used in data mining to identify patterns and structures in data, unlike traditional clustering algorithms that assign each data point to a single cluster. FCM allows for more flexible and nuanced clustering by assigning degrees of membership to each data point for each cluster. This allows data points to belong to multiple clusters simultaneously, which is particularly useful when the boundaries between clusters are fuzzy or overlapping. Fuzzy association rule mining. Association rule mining is a technique used to discover interesting relationships or patterns in transactional data. Fuzzy association rule mining extends this approach by capturing fuzzy relationships between items in the data. Instead of binary relationships, that is, item A is always associated with item B, fuzzy association rule mining allows for degrees of association between items. This enables the discovery of more meaningful and interpretable patterns, especially in cases where the relationships between items are not strictly defined or where there is uncertainty in the data. Overall, fuzzy logic plays a crucial role in data mining by providing a flexible and robust framework for handling uncertainty and imprecision in the data. Whether it's through fuzzy clustering algorithms or fuzzy association rule mining techniques, fuzzy logic enables more nuanced analysis and interpretation of complex datasets, leading to more insightful and actionable insights. Bayesian networks. Integrating fuzzy logic with Bayesian networks offers a robust approach to modeling uncertainty and imprecision in probabilistic reasoning. Bayesian networks are powerful tools for representing and reasoning about uncertainty in probabilistic systems. However, they typically rely on precise numerical probabilities, which may not always be available or appropriate, especially when dealing with uncertain or imprecise data. Fuzzy logic provides a framework for handling uncertainty and imprecision through linguistic variables and fuzzy rules, allowing Bayesian networks to model uncertainty in a more expressive and flexible manner. Fuzzy Bayesian networks. Fuzzy Bayesian networks combine the strengths of Bayesian networks and fuzzy logic. They incorporate linguistic variables and fuzzy rules into the probabilistic reasoning capabilities of Bayesian networks. This integration enables more nuanced modeling of uncertain systems by allowing for fuzzy representations of variables and relationships. Fuzzy Bayesian networks are particularly useful in domains where the available data is incomplete, noisy, or ambiguous, as they can capture and reason with uncertainty more effectively. Handling uncertain or imprecise evidence. Fuzzy Bayesian networks are adept at handling uncertain or imprecise evidence. Traditional Bayesian networks may struggle when faced with incomplete or noisy data, leading to less reliable inference results. Fuzzy Bayesian networks, on the other hand, can make use of fuzzy rules and probabilistic inference to make decisions even in the presence of uncertainty or imprecision in the evidence. This makes them well suited for decision-making tasks in real-world scenarios where the data is not always perfect. Overall, integrating fuzzy logic with Bayesian networks offers a powerful approach to modeling uncertainty and imprecision in probabilistic reasoning. By combining the strengths of both frameworks, fuzzy Bayesian networks provide a more flexible and expressive way to represent uncertain systems and make decisions based on fuzzy rules and probabilistic inference. Combining fuzzy logic with evolutionary algorithms indeed offers a powerful approach to optimizing fuzzy systems, such as fuzzy inference systems (FIS), for a variety of tasks. Optimizing fuzzy systems. Fuzzy systems, including FIS, rely on parameters such as membership functions, rule bases, and aggregation methods to make decisions or perform tasks. However, determining the optimal values for these parameters can be challenging, especially in complex systems or when dealing with uncertain or imprecise data. Evolutionary algorithms provide a solution by using techniques inspired by biological evolution to search for optimal parameter values through iterative optimization. Parameter optimization. Evolutionary algorithms can optimize the parameters of fuzzy systems by iteratively adjusting them based on a fitness function that evaluates their performance. This optimization process can involve fine-tuning membership functions, refining rule-based and optimizing aggregation methods to improve the overall performance and robustness of the fuzzy system. Handling complexity and uncertainty. Fuzzy evolutionary algorithms are particularly well suited for handling complex optimization problems involving uncertainty, non-linearity, and multi-objective optimization objectives. By combining the adaptive and exploratory capabilities of evolutionary algorithms with the flexibility and reasoning capabilities of fuzzy logic, these approaches can effectively navigate the search space to find solutions that meet the desired objectives, even in challenging and uncertain environments. Overall, integrating fuzzy logic with evolutionary algorithms offers a powerful framework for optimizing fuzzy systems for various tasks, including data mining, control systems, and decision making. By leveraging the complementary strengths of both approaches, fuzzy evolutionary algorithms can tackle complex optimization problems and improve the performance and robustness of fuzzy systems in real-world applications. Fuzzy logic offers valuable advantages when applied to pattern recognition tasks, especially in scenarios where uncertainty and ambiguity are prevalent. Handling uncertainty and ambiguity. In many real-world scenarios, data may not fit neatly into binary categories. Fuzzy logic allows for a more nuanced approach where patrons can be represented by degrees of membership in fuzzy sets rather than strict classifications. This flexibility enables fuzzy pattern recognition systems to handle uncertainty and ambiguity more effectively than traditional binary classifiers. Using fuzzy sets and rules, fuzzy pattern recognition techniques leverage fuzzy sets and fuzzy rules to represent patterns and make decisions. Instead of hard thresholds or boundaries, fuzzy sets allow for gradual transitions between different classes or categories. Fuzzy rules capture the relationships between input features and output categories in a flexible and interpretable manner, allowing for more nuanced decision making based on degrees of similarity or membership. Handling overlapping or ambiguous patterns. Fuzzy pattern recognition systems excel at handling overlapping or ambiguous patterns in data. Traditional patterns recognition algorithms may struggle when patterns are not clearly separable or when there is ambiguity in the data. Fuzzy logic allows for the representation of overlapping patterns and the incorporation of uncertainty into the recognition process, leading to more accurate and reliable recognition results. Overall, fuzzy logic offers a powerful framework for pattern recognition tasks by providing a flexible and robust approach to handling uncertainty and ambiguity in data. By using fuzzy sets and rules to represent patterns and make decisions based on degrees of similarity, fuzzy pattern recognition systems can achieve more accurate and reliable recognition results even in challenging and complex datasets. Fuzzy logic provides a flexible and powerful framework for handling uncertainty, imprecision, and complexity in data mining, Bayesian networks, evolutionary algorithms, and pattern recognition tasks. By integrating fuzzy logic with these techniques, researchers and practitioners can develop more robust, interpretable, and intelligent systems for a wide range of applications. Fuzzy logic can provide valuable contributions to various fields including computer vision, expert systems, robotics, speech recognition, and genetic algorithms. Computer vision. Fuzzy logic plays a significant role in enhancing computer vision systems by addressing the inherent uncertainty and ambiguity present in visual data. Handling uncertainty and ambiguity, visual data such as images or videos often contain uncertainty and ambiguity due to factors like variations in lighting conditions, occlusions, and noise. Fuzzy logic provides a framework to handle this uncertainty by allowing for gradual transitions between different categories or features rather than strict classifications. Image segmentation, object detection, and tracking. Fuzzy logic can be applied to tasks such as image segmentation, object detection, and tracking by defining fuzzy rules and membership functions to represent visual features and relationships. For example, in image segmentation, fuzzy logic can help delineate object boundaries by considering the degree of membership of pixels to different object classes. Similarly, in object detection and tracking, fuzzy logic can assist in reasoning about object characteristics and movement patterns in uncertain or dynamic environments. Fuzzy inference systems for image interpretation. Fuzzy inference systems, FIS, are employed to interpret and reason about image data, enabling more flexible and robust processing in computer vision applications. Fuzzy inference systems use fuzzy rules and membership functions to capture the relationships between input visual features and output decisions or actions. This allows for adaptive and context-aware image interpretation, where decisions are made based on the degree of similarity or relevance of visual features. Overall, by leveraging fuzzy logic, computer vision systems can effectively handle uncertainty and ambiguity in visual data, leading to more accurate, robust, and flexible processing in tasks such as image segmentation, object detection, tracking, and interpretation. Fuzzy logic is instrumental in the development and operation of expert systems, providing a means to capture and utilize expert knowledge effectively. Capturing expert knowledge, expert systems rely on the expertise of human specialists to solve complex problems. Fuzzy logic facilitates this by allowing experts to formalize their knowledge in the form of fuzzy rules and linguistics variables. Instead of rigid, binary rules, fuzzy rules can express expert knowledge in a more flexible and intuitive manner, capturing the uncertainties and nuances inherent in real-world decision-making processes. Flexible reasoning with fuzzy inference systems. Fuzzy inference systems serve as the backbone of expert systems, providing a flexible framework for modeling human-like reasoning and decision-making processes. FIS combine fuzzy rules, linguistic variables, and fuzzy logic operators to infer decisions or actions from uncertain or imprecise data. This flexibility enables expert systems to adapt to changing conditions and make informed decisions even in complex and uncertain environments. Applications in various domains. Expert systems incorporating fuzzy logic find applications in diverse domains such as medical diagnosis, financial analysis, and industrial automation. In medical diagnosis, for example, fuzzy expert systems can interpret symptoms and medical test results to provide intelligent decision support to healthcare professionals. Similarly, in financial analysis, fuzzy expert systems can analyze market trends and economic indicators to assist in investment decision making. In industrial automation, fuzzy expert systems can control complex processes and machinery by incorporating expert knowledge of system dynamics and constraints. Overall, fuzzy logic plays a crucial role in enhancing the capabilities of expert systems by enabling the effective capture and utilization of expert knowledge. By providing a flexible framework for reasoning with uncertain or imprecise data, fuzzy expert systems offer intelligent decision support and problem-solving capabilities across a wide range of domains. Robotics. Fuzzy logic is indeed a cornerstone in the field of robotics, offering robust solutions for control, navigation, and decision-making tasks. Fuzzy controllers for regulation. Fuzzy controllers play a vital role in regulating the behavior of robotic systems. These controllers adjust control parameters based on sensor feedback and task requirements, allowing robots to maintain stability, achieve desired performance, and respond appropriately to variations in the environment. Fuzzy control is particularly useful in situations where precise mathematical models are unavailable or when dealing with non-linearities and uncertainties inherent in real-world robotic systems. Adaptation to complex environments. Fuzzy logic enables robots to navigate and operate effectively in complex and dynamic environments. Traditional control methods may struggle to cope with the uncertainties and unforeseen situations encountered in real-world scenarios. Fuzzy logic, however, provides a flexible framework for reasoning and decision-making, allowing robots to adapt and respond in real time to changing conditions, uncertainties, and obstacles. This adaptability is crucial for tasks such as autonomous navigation, where robots must constantly assess and adjust their actions based on sensor inputs and environmental cues. Handling uncertainties. Uncertainty is a fundamental challenge in robotics, arising from sensor noise, environmental variability, and the inherent limitations of robot perception and action. Fuzzy logic excels at handling uncertainties by providing a means to represent and reason with imprecise and ambiguous information. Fuzzy controllers can effectively mitigate the effects of uncertainty by incorporating fuzzy rules and membership functions into their decision-making processes, enabling robots to make robust and reliable decisions even in the face of uncertainty. Overall, fuzzy logic is a powerful tool for enhancing the capabilities of robotic systems, enabling them to operate autonomously, adapt to changing environments, and make intelligent decisions in real time. By providing a flexible and robust framework for control, navigation, and decision making, fuzzy logic plays a crucial role in advancing the field of robotics and enabling the development of intelligent and capable robotic systems. Speech recognition. Fuzzy logic indeed offers significant benefits when applied to speech recognition systems, particularly in handling the variability and ambiguity inherent in spoken language. Handling variability and ambiguity. Spoken language is inherently variable and ambiguous, with variations in pronunciation, accent, and context. Fuzzy logic provides a framework to handle this variability by allowing for gradual transitions between linguistic categories and degrees of certainty. Fuzzy inference systems can model phonetic and linguistic uncertainties, enabling speech recognition systems to interpret and recognize speech signals more accurately even in challenging conditions. Modeling uncertainties. Fuzzy inference systems are well suited for modeling uncertainties in speech recognition by incorporating fuzzy rules and membership functions. These systems can capture the imprecision and ambiguity present in speech signals. This allows for more robust and accurate interpretation of speech, as fuzzy logic can accommodate variations in pronunciation, speech rate, and background noise, improving robustness in adverse environments. Fuzzy logic techniques such as fuzzy clustering and fuzzy matching can enhance the robustness and accuracy of speech recognition systems, especially in noisy or adverse environments. Fuzzy clustering techniques can help group similar speech patterns together, improving the system's ability to distinguish between different phenomena or words. Fuzzy matching algorithms can compare input speech signals with reference patterns in a more flexible and tolerant manner, mitigating the effects of noise and variations. Overall, fuzzy logic plays a crucial role in enhancing the performance of speech recognition systems by addressing the challenges of variabilities, ambiguity, and uncertainty in spoken language. By providing a flexible and robust framework for modeling linguistic uncertainties and handling adverse conditions, fuzzy logic techniques contributes to more accurate and reliable speech recognition capabilities. Genetic algorithms. Fuzzy logic can indeed enhance genetic algorithms (GAS) in optimization and search tasks. Genetic algorithms are powerful optimization techniques inspired by the process of natural selection. However, they can sometimes struggle with complex optimization problems or when dealing with uncertain or imprecise objectives and constraints. Fuzzy logic provides a more flexible and adaptive approach to optimization by allowing for gradual transitions between different solutions and degrees of membership in fuzzy sets, guiding exploration and exploitation. Fuzzy logic controllers can guide the exploration and exploitation of solutions in genetic algorithms by adjusting membership functions and fuzzy rules based on fitness evaluations. This adaptive control mechanism allows the genetic algorithm to strike a balance between exploring new regions of the search space and exploiting promising solutions, leading to more efficient and effective search processes. Handling complex optimization problems. Fuzzy genetic algorithms excel at handling complex optimization problems with uncertain or imprecise objectives and constraints. Traditional GAS may struggle when faced with objectives or constraints that are difficult to precisely define or evaluate. Fuzzy logic allows for a more nuanced representation of objectives and constraints, enabling the GA to adapt and respond to changes in the optimization landscape more effectively. Overall, integrating fuzzy logic with genetic algorithms offers a powerful approach to optimization and search tasks. By providing a more flexible and adaptive framework, fuzzy genetic algorithms can tackle complex optimization problems with uncertain or imprecise objectives and constraints, leading to more efficient and effective search processes and better solutions. Swarm intelligence. Fuzzy logic is indeed a valuable tool in swarm intelligence systems for modeling and controlling the behavior of individual agents within a collective system. Modeling and controlling individual behavior. Fuzzy logic provides a framework for modeling and controlling the behavior of individual agents within swarm, such as robots or autonomous vehicles. By defining fuzzy rules and membership functions, fuzzy logic controllers can guide the decision-making processes of each agent based on local sensor information and communication with neighboring agents. This allows individual agents to respond adaptively to their environment and coordinate their actions with other agents in the swarm. Guiding decision-making and coordination. Fuzzy logic controllers play a crucial role in guiding the decision-making and coordination of swarm agents. These controllers use fuzzy rules to interpret sensor information and determine appropriate actions based on the current state of the environment and the goals of the swarm. By considering local sensor data and communication with neighboring agents, fuzzy logic controllers can facilitate effective coordination among swarm members, enabling them to work together towards common objectives. Interpreting uncertain or imprecise data. Fuzzy inference systems are particularly well suited for interpreting and processing uncertain or imprecise data from sensors and environment feedback in swarm intelligence systems. By incorporating fuzzy rules and membership functions, these systems can adaptively respond to dynamic and unpredictable conditions, allowing swarm systems to adjust their behavior and strategies in real time. This adaptability is essential for swarm systems operating in complex and changing environments where precise information may not always be available. In summary, fuzzy logic enhances swarm intelligence systems by providing a flexible and adaptive framework for modeling and controlling the behavior of individual agents within a collective system. By guiding decision-making and coordination and interpreting uncertain data, fuzzy logic enables swarm systems to adapt and respond effectively to dynamic and unpredictable conditions, leading to more efficient and robust collective behavior. Transfer learning. Fuzzy logic indeed plays a crucial role in facilitating transfer learning by enabling the transfer of knowledge and insights from one domain to another, even when the domains have different distributions or characteristics. Knowledge transfer mechanisms. Fuzzy logic provides a mechanism for transferring knowledge and insights from a source domain to a target domain. This transfer is facilitated through fuzzy inference systems, which capture commonalities and relationships between the source and target domains using fuzzy rules and membership functions. By leveraging fuzzy logic, transfer learning algorithms can adapt and generalize knowledge learned from one domain to improve performance in another domain. Capturing commonalities and relationships. Fuzzy inference systems excel at capturing commonalities and relationships between domains, making them well suited for transfer learning tasks. By representing knowledge in terms of fuzzy rules and membership functions, fuzzy inference systems can identify similarities and patterns across domains, allowing for effective knowledge transfer and adaptation of models. This enables transfer learning algorithms to leverage existing knowledge to improve performance in new domains, even when the data distributions or characteristics differ. Identifying transferable patterns and structures, fuzzy logic techniques such as fuzzy clustering and fuzzy rule induction play a crucial role in identifying transferable patterns and structures in data. These techniques can identify clusters or groups of data points that exhibit similar characteristics across domains, facilitating knowledge transfer by identifying common features and relationships. By leveraging fuzzy logic techniques, transfer learning algorithms can identify relevant knowledge that can be transferred from the source domain to improve performance in the target domain. Overall, fuzzy logic provides a powerful framework for transfer learning by enabling the effective transfer of knowledge and insights across domains. By capturing commonalities and relationships between domains and identifying transferable patterns and structures in data, fuzzy logic facilitates knowledge transfer and adaptation, leading to improved performance in target domains with limited or sparse data. Adversarial learning. Fuzzy logic can bolster the resilience of models against adversarial attacks in adversarial learning scenarios. Dynamic adjustments of model parameters. Fuzzy logic controllers can dynamically adapt model parameters and decision boundaries based on adversarial inputs and perturbations. By leveraging fuzzy rules and linguistic variables, these controllers can make real-time adjustments to the model's behavior, effectively countering adversarial manipulations. This adaptability enhances the model's robustness by allowing it to respond to adversarial attacks with flexibility and resilience. Mitigating adversarial attacks. Fuzzy inference systems play a crucial role in detecting and mitigating adversarial attacks by analyzing the uncertainty and ambiguity in input data. These systems can identify suspicious patterns or deviations from expected behavior, flagging them as potential adversarial inputs. By incorporating fuzzy rules and membership functions, fuzzy inference systems can make decisions that prioritize model security and resilience, helping to thwart adversarial attacks before they compromise model performance. Handling uncertainty and ambiguity. Adversarial attacks often exploit uncertainties and ambiguities in input data to deceive machine learning models. Fuzzy logic excels at handling such uncertainties by providing a framework for reasoning with imprecise and ambiguous information. Fuzzy inference system can leverage fuzzy rules and linguistic variables to assess the uncertainty associated with input data, enabling models to make more informed decisions in the presence of adversarial attacks. Overall, fuzzy logic offers a powerful toolset for enhancing the robustness and resilience of models against adversarial attacks in adversarial learning settings. By dynamically adjusting model parameters, detecting and mitigating attacks, and handling uncertainties in input data, fuzzy logic strengthens models' defenses and helps safeguard against potential vulnerabilities posed by adversaries. Quantum computing. While quantum computing and fuzzy logic are distinct fields, there is a potential for their intersection, particularly in the realm of quantum computing interaction and accessibility. Modeling quantum states and operations. Fuzzy logic could potentially be applied to model and represent certain aspects of quantum states, operations, and measurements. Quantum systems often exhibit complex behaviors that can be challenging to describe using traditional mathematical formalisms. Fuzzy logic could provide an alternative linguistic and intuitive framework for describing these phenomena, potentially offering new insights into quantum systems behavior. Describing complex quantum phenomena. Fuzzy logic could indeed offer a linguistic and intuitive framework for describing complex quantum phenomena, making it more accessible to researchers and practitioners. Quantum mechanics is famously counterintuitive, with many of its concepts defying classical intuition. Fuzzy logic could help bridge this gap by providing a more intuitive way to reason about quantum systems, potentially aiding in the interpretation and understanding of quantum phenomena. Interpreting quantum data. Fuzzy inference systems could be used to interpret and analyze quantum data, potentially making quantum computing more accessible and understandable to non-experts. Quantum computing involves manipulating and mirroring quantum states, which can produce complex and noisy data. Fuzzy inference systems could help extract meaningful information from this data by interpreting it in a linguistic and intuitive manner, potentially facilitating communication between quantum computing experts and non-experts. While these ideas present intriguing possibilities, it's essential to note that the integration of fuzzy logic with quantum computing is still largely speculative and requires further research and exploration. However, leveraging fuzzy logic's linguistic and intuitive framework could potentially offer new insights into quantum phenomena and help make quantum computing more accessible and understandable to a broader audience. Overall, fuzzy logic offers a versatile and adaptable approach to addressing complex and uncertain problems in artificial intelligence, including swarm intelligence, transfer learning, adversarial learning, and quantum computing. By integrating fuzzy logic with these areas, researchers and practitioners can develop more robust, flexible, and intelligent artificial intelligence systems capable of handling diverse and challenging scenarios. Fuzzy logic can indeed play a key role in the development of cognitive computing, game theory, and augmented virtual reality applications. Cognitive computing. Fuzzy logic serves as a foundational element in cognitive computing which seeks to emulate human-like cognitive processes in machines. Representation and reasoning with uncertain information. Fuzzy inference systems are fundamental components of cognitive computing, providing a mechanism for representing and reasoning with uncertain or imprecise information. This capability closely mirrors human decision-making processes, which often involve dealing with uncertainty and ambiguity. Fuzzy logic allows cognitive computing systems to make decisions based on degrees of truth rather than strict binary classifications, enabling more nuanced and human-like reasoning. Applications in natural language understanding. In natural language understanding tasks such as language translation, sentiment analysis, or chatbots, fuzzy logic plays a crucial role in capturing the inherent ambiguity and variability of human language. Fuzzy inference systems can interpret and process linguistic inputs, allowing cognitive computing systems to understand and respond to natural language queries in a manner that closely resembles human comprehension. Pattern recognition and decision support systems. Fuzzy logic is also instrumental in pattern recognition tasks such as image recognition, speech recognition, and handwriting recognition. By incorporating fuzzy rules and membership functions, cognitive computing systems can identify and interpret patterns in data, even in the presence of noise or uncertainty. Additionally, fuzzy logic is utilized in decision support systems to aid in complex decision-making processes by considering multiple factors and uncertainties similar to how humans make decisions. Overall, fuzzy logic is a foundational component of cognitive computing, enabling machines to emulate human-like cognitive processes such as reasoning, understanding, and decision-making. By providing a mechanism for representing and reasoning with uncertain or imprecise information, fuzzy logic enhances the capabilities of cognitive computing systems across a wide range of applications, including natural language understanding, pattern recognition, and decision support. Game theory. Fuzzy logic indeed plays a significant role in game theory, particularly in modeling decision making and strategy selection in both competitive and cooperative environments. Modeling decision making and strategy selection. Fuzzy logic provides a powerful framework for modeling decision making and strategy selection in games. Fuzzy logic controllers can represent the uncertainty and imprecision inherent in players' strategies and preferences. This allows game designers to create more realistic and adaptive game dynamics where players' decisions are influenced by a multitude of factors, including their own certainty about the game state and the strategies of their opponents. Representing uncertainty and imprecision. Fuzzy logic controllers are adept at representing uncertainty and imprecision in players' behaviors and preferences. In game theory, players often make decisions based on incomplete or ambiguous information, and their preferences may be influenced by a range of factors that are difficult to quantify precisely. Fuzzy logic allows game designers to model these uncertainties using fuzzy rules and membership functions, leading to more realistic and nuanced game experiences. Enhancing realism and engagement in multiplayer games. In multiplayer games, fuzzy logic can be applied to model players' behaviors, emotions, and reactions, enhancing the realism and engagement of the gaming experience. By incorporating fuzzy logic controllers into non-player characters, NPCs, or game environments, game designers can create more dynamic and responsive game world where NPCs exhibit human-like behaviors and emotions. This enhances the immersion of players and make the gaming experience more compelling and interactive. Overall, fuzzy logic provides a valuable tool for enhancing game theory by modeling decision making, representing uncertainty, and creating more realistic and engaging game experiences. Whether in competitive or cooperative environments, fuzzy logic enables game designers to create more dynamic and adaptive game worlds that respond to the complex and nuanced behaviors of players. Augmented virtual reality (AR/VR). Fuzzy logic plays a crucial role in enhancing augmented reality (AR) and virtual reality (VR) applications by addressing uncertainties and ambiguities in sensor data, user interactions, and environmental conditions. Handling uncertainty and ambiguity. AR/VR environments often involve dealing with uncertain and ambiguous sensor data, user inputs, and environmental conditions. Fuzzy logic provides a robust framework for handling the uncertainty by allowing for gradual transitions and degrees of membership in fuzzy sets. By incorporating fuzzy logic, AR/VR systems can better interpret and respond to uncertain or ambiguous information, leading to more immersive and reliable experiences. Adapting system behavior. Fuzzy controllers are instrumental in adapting the behavior of AR/VR system based on real-time feedback from sensors such as cameras and inertial measurement units (IMUs). These controllers can dynamically adjust system parameters and decision-making processes to improve the accuracy and responsiveness of AR/VR experiences. For example, fuzzy controllers can optimize tracking algorithms to better estimate the user's positions and orientation in the virtual environment, enhancing the overall quality of the AR/VR experience, analyzing spatial and temporal data. Fuzzy logic techniques such as fuzzy clustering and fuzzy inference can be employed to analyze and interpret spatial and temporal data in AR/VR environments. For instance, fuzzy clustering algorithms can help segment and classify objects within the virtual environment, improving scene understanding and object interaction. Fuzzy inference systems can also interpret user gestures and actions, enabling more natural and intuitive interaction with virtual objects and environments. Overall, fuzzy logic enhances AR/VR applications by providing a robust framework for handling uncertainty, adapting system behavior, and analyzing spatial and temporal data. By incorporating fuzzy logic techniques, AR/VR systems can offer more immersive, responsive, and interactive experiences, ultimately enhancing user engagement and satisfaction. Fuzzy logic plays a crucial role in cognitive computing, game theory, and AR/VR applications by providing a flexible and robust framework for handling uncertainty, imprecision, and complexity in data and decision-making processes. Its ability to model human-like reasoning and adaptability makes fuzzy logic a valuable tool in developing intelligent and interactive systems across various domains. Fuzzy logic plays a pivotal role in artificial intelligence by providing a flexible and robust framework for handling uncertainty, imprecision, and complexity in data and decision-making processes across various domains. Its key contributions can be summarized as follows. Handling uncertainty. Fuzzy logic excels in situations where data or knowledge is uncertain, incomplete, or imprecise. By representing uncertainty using linguistic variables and fuzzy sets, fuzzy logic allows artificial intelligence systems to reason and make decisions in ambiguous and uncertain environments. Interpretability and explainability. Fuzzy logic provides transparent and interpretable models, making it easier for humans to understand and trust the decisions made by artificial intelligence systems. Fuzzy inference systems produce linguistic explanations, enabling users to comprehend the reasoning behind AI-generated outputs. Flexibility and adaptability. Fuzzy logic offers a flexible and adaptive approach to artificial intelligence, allowing systems to handle nonlinear relationships, dynamic environments, and changing requirements. Fuzzy inference systems can dynamically adjust their parameters and rules based on evolving conditions, making them suitable for real-world applications. Integration with other techniques. Fuzzy logic can be seamlessly integrated with other artificial intelligence techniques, such as neural networks, genetic algorithms, and Bayesian networks, to enhance their capabilities and address complex problems more effectively. By combining fuzzy logic with other techniques, researchers and practitioners can develop more robust, intelligent, and versatile artificial intelligence systems. Applications across domains. Fuzzy logic finds applications across a wide range of domains, including robotics, control systems, decision support, pattern recognition, and natural language processing. Its versatility and applicability make fuzzy logic a valuable tool in developing artificial intelligence systems for diverse applications and industries. In essence, fuzzy logic plays a pivotal role in artificial intelligence by providing a principled approach to handling uncertainty, interpretability, adaptability, and integration across various domains. Its ability to model human-like reasoning and decision-making processes makes fuzzy logic a foundational technique in development of intelligent and autonomous systems. Stay updated with advances in fuzzy logic. Keep up with the latest research and advancements in fuzzy logic and its applications in artificial intelligence. Join fuzzy logic communities. Participate in forums, communities, and discussions related to fuzzy logic and artificial intelligence to connect with experts and enthusiasts. Build a portfolio. Showcase your projects and implementations in a portfolio to demonstrate your skills to potential employers. Networking and collaboration. Connect with professionals and researchers in the field through networking events, conferences, and collaborative projects.